I am very passionate about this video. Okay, logarithmic scales are really, really useful. And here's why they're useful. I'm gonna give you a little graph here. Let's look at the graph of 2 to the x. Now, we did a section on graphing exponential functions. And the interesting thing about graphing exponential functions is you probably notice the same thing, is that they're hard to graph. Because it's hard to get meaningful data on a picture, right? Like, sure, this data tells us, like, so once we're here, we can start reading the data, and then like up to here, and then we go off. But either it's hard to read the data for small, or it's hard to read the data for big. We can't get both, right? Like if I want to stretch this graph out, then it makes it even harder to read numbers at the left. So if I asked you, for example, if I didn't tell you what this function was, if I just wanted you to read this graph and say, all right, looking at this graph, what's the function value at -3? We just can't. Function value at -4, I don't know, it's close to 0, but we lose meaningful information. Similarly, if I gave you this graph, no function, if I gave you this graph and said, what's f of 5 or f of 4, you'd have no clue what f of 4 is. It's not on the graph. It doesn't fit. This graph is only helpful for a little tiny amount, and it's impossible for us to change our scale. It's impossible to change our scale to include meaningful data at -4 and +4. So that's what logarithmic scales are all about. Watch this. If y equals 2 to the x, this is hard to graph. Hard to show meaningful data on a graph. And let's just say, add an example, -4 and +4. There's no way to show meaningful information of both of these. Because again, if we made y be really small, like let's look at y from -0.1 to +0.1. Oh, now I can see -4, what's going on here. But of course I can't see anything at +4. Or again, if I did the opposite and made y be really big on our scale, well, now I know what's happening at +4, but I certainly have no clue what's going on over here. You can't do both. It doesn't matter how we adjust our scale. We cannot see both. So what we do is something called a log scale. We don't look at y anymore. We look at the logarithm of y. Well, that's going to equal the logarithm of 2 to the x. We take the logarithm of both sides and simplify the right. Properties of logarithms tell that this is just some number times x. This is just some number. And this is what log scales are all about. We look at this new variable, we call it y, capital Y. Now, even though this graph is hard, the graph of capital Y, which is just some number, times x, is a line, and it shows very meaningful data. Let's look at this new graph. In the old graph, we couldn't figure things out about +4 and -4. But in this new graph of x times the logarithm of 2, now if we look from, say, -5 to 5 or something, this graph, look, I can see what this graph is at 4. Oh, it's about 3.5. And at -4, oh, it's about -2.5. Sorry, 2.5. +2.5 and -2.5. I could see it even better with a different scale, right? Wait, I said 2.5. That wasn't right either. At +4, it's about a little over 1. About 1.5. And at -4, it's about -1.5. So now we can read this graph. Now we can read data. This is easy to graph. And that's what log scales are all about. And not just easy to graph, but easy to read the graph. So if we're using Desmos, right, that other situation didn't really matter that we couldn't read it because we can just click on a point. But if we're looking at if we're making a PDF, if we're writing an article, like let's say I'm writing or reading an article on exponential growth of, a COVID population, like early on in the pandemic or something, and it has an exponential growth. Well, if I want to see meaningful data, that's going to be hard to read. They're not going to be able to choose something for the page that makes it easy to read, other than just saying, oh, this is really steep, which is actually what everyone did. But if you want meaningful data, you could actually graph the logarithm of that value. And that's what we're doing here. And then you can read a graph and get data from that graph. Okay. And that's called a semi-log plot, by the way. What we just did. This is called semi-log plot. I don't think this is really covered in the book. All right. Because X is a normal variable, capital Y is a log. So it's one of them is a log, one of them is not a log. If we had the log for both, it would be a log-log plot. But anyway, we won't talk about that too much here. Example 7. Find the values on the logarithmic scale below. So these right here, I'm showing you the logarithm of X. So this is not a number line showing values of X. This is a number line showing you the values of the logarithm of X. Let's say one of them is right here. And one of them is right here. So to find the values of these, right, these can be thought of as our X values. Sorry, no. Those are not the X values. We are curious about the X values. These are the logarithm of that X, right? This is not the value of X. We can't draw the value of X, just like we did over here, right? We could look at the logarithm of Y, but we couldn't actually look at the graph of just Y itself. So here we're plotting points, but we can't plot X itself. If we plotted X itself, we wouldn't be able to make it very clear. We're trying to plot the logarithm of X to meaningfully have readable data. So our 2 points are the log of X equals, well, this is -1, -2. This is about -2.5. And the other one, that's 2 right there, has a logarithm equal to 2. What is the value of X? Got to solve a logarithmic equation. Whoa! This is an application of logarithmic equations. Convert it to exponential form. 10 to the -2.5 equals X. 10 to the -2.5. That's about 0.00316. This is X is equal to 10 to the squared. Is X equals 100. This is why log plots are so useful. Imagine trying to plot these two numbers on a number line, 100 and 0.00316. You could not plot both of these on the number line. Like, I guess you could, right? All right, 0's here, 100's here. Well, then we got 100 smack on the dot and something really close to 0, but you can't give meaningful accuracy for both. All right. That's what log plots are all about. Log scales are all about is if our data, some of our data is really precise and small and some of our data is really big, we can use a log scale to show both of these things. All right, example 8. Write the approximate intensity of sounds on a log scale. Here, I want you to plot sound of a whisper, which is about 10 in the negative tenths W over M squared. Sound of a vacuum cleaner, an average vacuum cleaner, which is 10 to the negative fourth W over M squared. And the sound of a jet, which is on average going to be 10 squared W over M squared. All right. We cannot plot all of these on a regular scale, right? This is so close to 0. This is pretty close to 0. And this is 100. Can't plot all of these on a regular scale, but we can plot their logarithms. Let's look at a scale. Let's look at the common log of x. Well, what is the logarithm of all of these? The common log of this x, what is that? It's negative 10. The common log of this x, it's negative 4. And the common log of this x is 2. So we can't plot these numbers, but we can plot their logarithms. And that's what we're doing here. We just need some scale that goes from negative 10 to like 2. Let's look at 0b here, and then negative 1, 2, 3, 4, 5, negative 6, 7, 8, 9, 10. Oops. Let's go a little further. All right, and now we can plot it. The whisper on the log scale is at negative 10. The vacuum cleaner on the log scale is at negative 4. And the jet on the log scale is over here. That's why log scales are neat. They allow us to graph data in a readable format, even if some of the data is really big and some of the data is really, really precisely small. Okay? Let me know if you have any questions. I really like this stuff, so I'd be more than happy to talk about it if you had some. Have a good day or night. A lot of people work on this at night. Have a good night, okay? Have a good morning. Is it 2 in the morning over there? Hopefully not, but maybe. Bye-bye.